eighth iFi Journal Club of the semester. And today we're happy to have Thomas telling us about how to apply deep learning to numerical relativity.
Oh,
Take
great.
it away.
Thanks for giving me the opportunity to talk. I'm going to give you a slide setup. First of all, in case you forgot about gravitational waves, right? Typically, where they're being produced is in binary black holes. They in spiral and then produce in the process gravitational waves. As they pass through us, like if you have a circle of stone and a gravitational wave passing through, the effect on this one is effectively wobbling, and that's roughly it. However, this is extremely exaggerated movement. So of course you need like some really fine lasers that measure distances very accurately to capture this signal. And so there's of course some the detectors have been built, one in Virgo, and you have the central facility there, and lasers are being shot out, reflected in the end. It's very high-tech simulation, and bounce back. There's of course one in Livingston, Louisiana. I mean, and these are hypersensitive facilities, right? So even like wind blowing on the local trees is a noise source. At some point, I think graduate students running too hard around the laser facility was also a potential noise source. The noise was really a massive issue. You can even see like waves hitting the North American continent. Yes, really, really hyper accurate. This one is the LIGO Hanford. This one I could even visit. It's in the middle of desert and described in a podcast as the most toxic place in America because there's like a nuclear dump below that. So if I blow up it, ignore it. But there's of course there's a shield around the one you see, a concrete shield. And inside you have these tubes, which are vacuumized tube where the laser shoots back and forth. And at the end you have the huge laser that reflect everything back. And I mean, just to tell how sensitive these are, like quantum effects of these 40-kilogram mirrors are relevant and have an effect on the measurement. That's really unbelievably sensitive. How do we know now that these are just some time domain signals from all three detectors? That this one corresponds to roughly like a black hole with one black hole being 30 solar masses, the other also roughly 35 solar masses, and roughly 410 megaparsecs by just looking at a bunch of these signals. It's of course big old inverse problem. You do a bunch of simulation. This is what my job is. And then you get many waveforms from these simulations. And of course, doing some MCMC, you can figure out that these are indeed the parameters of the binary black hole merger.
Can I ask a question?
Yeah.
So I see like at 0.4 seconds, the two detectors are aligned, but everywhere else they don't look aligned at all.
You mean so this one? I think this one they shifted the signal because I think they took into account effectively the speed of light travel time between the detectors.
Right. So at 0.4, they look almost on top of each other. But then everywhere else in time, they look like they're completely uncorrelated. Is that some systematic noise, or
this is just noise of the detectors, and that's why you need like three different, because there's so many noise sources. If you don't see nothing correlated between the detectors, right, like it's most likely noise, because that's a massive thing. And I mean, one thing, and of course, how do you simulate this one? Like, of course, the Einstein field equations are kind of useless for us numericists because there's no time and space explicitly. So what you have to wait is another 50 years until somebody finds the ADM decomposition. On the topic of horrendous partial differential equations, I don't want to talk about them. Just want to show how horrible they are. And if you put them into a computer, they're also highly unstable. So you have to wait another 50 years that somebody comes up with a stable formulation for that one. This is currently the BSSN one of the state-of-the-art formulations that we are currently using. So simulating these black holes is really hard, really difficult, and that's the major point. Here is an example of a simulation. You can see the two binary black holes, and below there you can see the time domain signal. I can jump here a bit in, and you can see the two black holes. Sorry for the bad frame rate. So this, of course, are the apparent horizons, not completely the real horizons. And now, as they're getting closer, you can see the gravitational wave signal becomes higher and higher frequency. And at the peak, roughly at the peak, not completely, they form a new common horizon, which create like a highly perturbed black hole. And then you can see the exponential decay of the gravitational wave signal in the end. So, and here you can see now also the gravitational waves being propagated out. And however, what I want to fundamentally say, we are still very much at the beginning, like, right? We had just built the first detectors, and one thing what is really easy to eliminate noise, especially seismic noise, is you just take everything and shoot it into space. So that's the ELISA space mission. That's gonna be 2034-ish, something like that. Or other like next generation ground-based detector, which effectively are just what we already have, just bigger, just 10x bigger effectively. So we will have exponentially better gravitational wave detectors in the future, and we will measure almost every binary black hole in the observable universe. So we really highly accurate measurements that we can do. Just here you can see just a difference of the signal. That's what we're going to observe. And one is LIGO A+, which is not actually the configuration we have. It's a future, it's of an upgraded version of our current detectors, and versus Cosmic Explorer, which is one of the next generation detectors. And I mean, the noise, the amount of noise is just a different level. And currently, the situation is the following, roughly. We have detector noise and we have some model noise coming from simulation, and we still don't run into any issues because detector noise roughly matches model noise. However, for next generation detectors, right, it's an exponential improvement. It's hard to understate how much better they're gonna be. We might run into this issue that detector noise might be much better of what we actually can simulate, which would be a massive bummer because like these are billion-dollar investments and we cannot fully use them just because we're not good at simulation. So as numerical relativists, we have to shape up a bit. Yeah.
What's the improvement in model noise? Like,
So we're gonna have some Moore law improvement, just assuming current codes a bit. And I mean, assuming CPUs will be better, but we will likely have to do better than that.
So the improvement is just having more computes, not?
Yeah, more compute effectively. But yeah. So of course now this was all a motivation why you want to do ML. Normally it's a harder sell, but this is a nice crowd where it's hard. It's easier to sell to use ML to solve problems.
Is there like a particular regime where this is more the case than others? Like
so there's specific
equal
parameter.
mass,
Yeah,
same
exactly.
mass.
Yeah, especially for high mass ratio.
Okay.
This is where for high mass ratio simulations, which are very interesting, of course, this one is especially one parameter space that is especially interesting. Yeah, and of course high spin too, right? Equal mass effectively should be fine. Equal mass, no spin. But if you go in these other regimes, it's getting significantly more difficult.
Okay.
And of course, the general one motivation is also we are working always with HPC, even before HPC was all CPU based in the before times. And now, well, it's not going to be anymore. And so to have algorithms that can use this new computer architecture, ML is, and deep learning specifically, is a natural choice. Now, give you an idea of how we want to solve this. My current belief is that just chugging out current solvers is probably not what is worth. So currently we have this true underlying solution that we will never have, And typically with numerical solvers, we are approximating and build up error as we go. Now, there's some cool tricks you can now do nowadays to get rid of this error. Some before any machine learning, people use that cool trick. So you use a similar solution that you know the analytical solution for, which in general relativity there exists a lot. And so you do a numerical step, and then you get the correction, and you just add it up to your simulation, which is kind of similar, and then effectively get closer to the original solution. You do this a bunch of times, and effectively what you get here is a more accurate simulation to what you had before, right? A numerical. People did this. There's a cool paper. It's very simple, no ML. Effectively, you have here a big black hole, and here you have a tiny black hole that you barely can see, which looks effectively like just a big black hole, which is a known analytical solution because it just sits there and doesn't do anything. So estimating numerical error for that one is really, really easy. And so you can do the simulation and effectively remove all of the noise. Old trick, but I mean, it only works for something where you're very close to analytical solutions. And I did my own test, of course, like really simple, right? An advection equation, which is the most simple equation you can come up, and using a very terrible numerical scheme to show how much, this is no correction. You can see that the solution, the numerical solution really collapses. And if I'm then, and if I learn this correction with a deep learning algorithm, cool, it works well. Was very happy. I applied for a fellowship, got a fellowship, and now I have to do the hard work. Now what I don't have, of course, is typically I don't have the underlying true solution. So what I have to do instead, so I still have my low resolution simulation, but then to create a ground truth, I have to do a high resolution simulation. Not ideal, but for data generation, maybe good enough. At least I thought initially. Spoilers. Now I have to scale everything up. Before I did one dimension on a super easy simulation. Now I have to do it in 3 dimensions with 25 coupled different fields, so a bit harder. And I got going. Like I started building it. It's after my C++ solver where I generate data. I have to create a pipe process out of that data, which because generativity is very. Then I have a network that learns everything, and then I have had to build like a C++ PyTorch interface where I put the network back into my BD server. So massive construction network, and what I ended up with was like this. It looked really cool, but highly impractical and not really useful. Mostly because it was it used a lot of fuel. And the fuel was, of course, as mentioned, the high resolution data, right? To really get this going, I needed a lot of high resolution data, which means running simulations at really high resolutions, which is expensive in the first place. And I'm not OpenAI, I'm a poor academic, so I can't do that. So I have to smarten up. And the question is, can we survive without HR data? Just effectively like bootstrapping the whole thing. And so what you have to do is you have to stare at all of these poor equations. And I don't want to stare you too hard because this will hurt your eyes. You are going to have some set of equations, which are these ones, which have these shapes, right? They're just a time derivative. And effectively, these are your evolution equations. They tell you on how to go from t equals 0 to t equal 0.2. These are nice, but then there are these weirdos, which these ones are great because like they are effectively checks, right? So you apply them to one specific time, and they have to be either not fulfilled or the left-hand side equal to right-hand side, or not. So mathematically, if you have any solution of generativity, these equations will always be fulfilled because we're doing numerical stuff. They typically only approximately fulfilled. So I mean, this is pretty cool, right? We can effectively, what we can do is like we create these two measures. We put left-hand side minus right-hand side and check on how well these are fulfilled. These effectively, these are not exactly energy and momentum constraints, but they're kind of energy momentum constraints for space-time. And what you do, you chuck them into a loss, and we solved our problem, maybe, that we now can, instead of doing, we don't need the high resolution anymore. We can just effectively apply this loss that doesn't require any high resolution simulation anymore. And we're maybe good. And so I applied this.
Before you go on,
Yeah.
let me just make sure I understand what you're doing. So you are you're running your DT, you're running your
Yeah.
solver, but it's a discretized solver.
Yeah.
And then the goal is to estimate the error and correct for it. And before you were estimating it by comparing it to some known analytic solution, then you did, I'm gonna do this high resolution thing, and now you're gonna choose basically, but this is a mapping from, like you do a forward step and then you choose a map that kind of correct it.
Exactly.
And this is the correction. So can I ask?
Yeah.
Is it possible to change the time step itself? That is, there's truncation errors in the code. So you could have just said, look, I have these truncation terms, which you're setting to 0. But you could have just said, no, I'm going to keep those terms. In fact, I don't know what they are. And I could just choose their values such that when I take a time step, I can minimize that as opposed to putting a correction afterwards.
Yeah, there would be also possibility. Like I chose to do the correction afterwards just because in that ways the computational engineering was easier. I wanted to avoid in the end, what I also realized, because I made this huge loop where I interacted with the C++ underlying C++ engine, it was really hard to do this, right? After I generated data, trained everything, it was really difficult. And so what I decided, if I do it like this, I can just generate the data at once and then do everything offline effectively without this involving the solver, and just acting on the data offline and just do the correction afterwards. So, and then it was mostly an engineering answer, because in the end I wanted to get something going, and yeah.
And so then maybe just to make sure I understand what the correction term is. The correction term is a function of what? Is it a function of both the starting point and the ending point of a given step, or just the ending point of the step?
It's just the ending point of the step. I figured I've tried both, and I think in the end, I think it didn't matter too much.
It didn't matter.
I think at this time, I think it was early tests, so maybe if I repeat them, I'm not sure anymore. But I think at the end, I think the ending step was good enough at the moment. Maybe this, as I'm scaling, this might make a difference. But for at this time when I was trying it out, it didn't matter.
Right, because if it were a function of both the beginning and the ending step, then basically you're just learning a better step.
Yeah.
But here it's somehow you're learning how to get back to the manifold of constraints.
Yeah, and then I can do some trickeries, because and that's one I'm slight foreshadowing.
Yeah.
It turns out the real solution, of course, lives on this manifold.
On the manifold of zero loss.
Of zero loss. And so if you do some smart things, you might be able to get the underlying truth under read. But this is a foreshadowing what comes later on. So
can you get back to that actually?
Oh yeah, please.
These are like, you're doing an MSC type loss for these constraints, right?
Yeah.
And could you also do like a Lagrange multiplier type loss where this is not quadratic but rather like linear in the?
Sure. Yeah. I mean, I've just used this one because this was the easy, obvious step. I've not tried any other version. I could have done L1. I mean, Lagrange multiplier, then I would have I would want to minimize with a constraint. But in this case, I'm good enough just to minimize, because I will never actually truly fulfill these ones. This is numerics. The best I can do is minimize them. But yeah. All right. And okay. Any other questions? I like in between questions much. And so okay, first of all, now what we now don't have, right? Like we don't have any ground truth solution, right? And maybe this is we don't have any high resolution, and so effectively we're just working with the low resolution per se. So to fully again to just emphasize to just make it more visible to what I'm actually doing, right? This is the constraint surface that where the constraints are fulfilled. And my true solution, of course, lives on that surface. It's always a bit harder to represent things. Of course, I don't know the true solution, so I have to remove this. So what I'm doing is I'm taking a step, and the network just brings me effectively back to the constraint surface. And as I do this, I get something hopefully that approximates better my true underlying solution. Now,
Is there a notion of closest approach?
yes, you're coming exactly to the problem that I'm having, right? There's many ways of getting back to the surface. And so of course the easiest way is to find the closest one. And so how do I do this? This is now a bit of a trickery and involves some PD ideas. So I have my X and here typically I use then a correction network, as we said, for the end after the step, to then get the correction and then add it back and add it back up. I use a CNN because I got true equivariance from general relativity. I can have more symmetries like rotational and stuff that I could put in, but I didn't do that. But there's more symmetries to be used. And so I build it, and so if I and if you look at these ones that I zoom out the delta X, wait, come on, wait. And so what I can do here is, this is my correction. What I'm now doing a training, I'm introducing some masking. So how does the masking help me to get back to make sure that I get the smallest possible correction? Is first of all, here I use a random mask, and what will happen here is here I have derivatives that I still have to approximate. And by masking, what I'm effectively, if I mask half of it and delta X is very large, all of my derivatives will effectively explode. So by just simply masking, and I figured, okay, it's not truly random masks that work well, but masking out every 1/4 element and then shifting the mask around a bit, that turns out to be the best case. But by making derivatives grows, the momentum goes big, and thus also my loss goes big. So just by masking, I can disincentivize solution where I take larger steps. And so this kind of works well. And I mean, also, does it work like on performance-wise? And also, does it generalize? That is really important. Generalization is the most important thing, because I will never simulate my training data again. Whenever I simulate, I do another simulation that has different parameters. So real fundamental question, am I generalizing well? So here is a normalized baseline, right? So if you're below 1, you effectively do better than the baseline, which in this case is some interpolation, some simple methods, what I'm currently using in the code. And here you can see this is the performance of my validation data set for the simulation that I used. I only used one simulation for my training data, and I do like, of course, 100 times better. But I mean, it's the validation set, so that's never what I'm gonna see. So again, single simulation training data. This is a very special case that in a real case, I would have to use multiple simulation actually. So if I change my black hole mass for my simulation by like 4%, I of course have a decrease in performance. If I increase it by 10%, I'm still doing something. I'm still 10 times better than the baseline. And as I get further and further, I get worse and worse performance until roughly 40%. I mean, it's pretty cool. First of all, it's pretty cool that I get a random power law again. This seems to happen seemingly in neural networks. And yeah, so this is pretty exciting. And then it actually it does generalize to some degree, which is great. And so of course, in the real case, I have multiple simulation, and then the performance wouldn't fall apart as much. And especially in the use case that we're looking, which is parameter searches, where I need to simulate many of these binary black holes. This is the more likely case that would be working with. One thing that is really cool too, like these networks, typically when you compute this, we split our simulation up and separate it on many compute units. and I can evaluate on each compute unit the network separately. There's no communication between them. That is really important because just because adding communication is super technically hard. And what I want to do with this project is something that concretely can be applied. I just didn't want to just strap a random network and just hope it produces anything. I wanted that this one at least can actually have an effect on current day state-of-the-art numerical relativity codes. And so this was a crucial point that was very important. Now, okay, all is working, all is beautiful, but can we do better, right? Before I was saying, like, when we looked before, right, there's many ways to get back to the surface. But maybe the shortest one is not necessarily the best one, right? The true underlying solution might not be the shortest one, it might be maybe the second shortest one. So could we technically find this?
Just a question. So if someone hands you a solution, like they said, I've done my calculation, here it is. Is there a number that you can assign to that solution that says this is a good solution or not? So if I understand correctly, each time step you can do these constraints.
Exactly.
And presumably you could also just verify, hey, were the time steps done correctly? But is there a notion of success that I can assess after the fact?
I mean, after you've done the time step.
So I'm imagining, you know, someone says to you, hey, I've done this amazing calculation, and you want to check whether they've done a reasonable job. Is there a way for you to check after the fact kind of how accurate what they're doing is?
I mean, if I have the full solution, right, all of the time steps, I can just evaluate this equation and just say, like, hey, we at least are on constraint, and this is a high quality simulation. Now, to truly know if this is a good solution, because that just checks, again, am I a constraint surface or not, doesn't mean I've got the right solution. Typically, what we do as numerical relativists, we just run everything at higher resolution and check for a convergence in the solution to something, to something. That's typically how we truly would 100% check it. But constraint surface is like a necessary condition, effectively, to say that you're good. If you, yeah.
Okay, but if I understand correctly, like the constraint surface, that's done each time step you say, am I on the constraint?
Each time step, I can just continuously check I'm in my simulation if I'm doing great or not. Yeah.
But if I want to know, like from one time step to another time step,
yeah,
and I want to say, well, did I do a good job in going from t=1 to t=2?
Yeah.
That is there a quality criteria associated with that people would agree on?
You need to convert. If you okay, first of all, you can always just check, like, does the second one fulfill after time step, do I still fulfill it?
Sure.
And that's always one, but of course, otherwise you just have to convergence check, which means you just have to run everything at higher simulation and see that it's converging to something reasonable. And there's of course a bunch of papers that didn't do convergence testing and found new cool physics that then went away in convergence testing. That these things happened. Yeah, this is the hard. This may be right. Like, in a way, constraint surface is cool, but it's not everything. And maybe what I was hoping, maybe you can do some trickery to get there, right? And so because
in my brain, so. I don't know if this is a sensible question, but what is the dimensionality of the whole space versus the dimensionality of the constrained surface? Is this I have 50 equations and I have one constraint.
Yeah, totally. So
I
have 16. There's in total 25 variables, but the ones that some of them are gauge variables, so they are not relevant, they're pure true choice, effectively choosing how the observers are moving. There's 16 variables that I have that they're not gauge, and from these 16 variables, those 17 I forgot now. We have 4 equations. This is the dimensionality of it.
So those areas that you're drawing, there's actually a lot of different directions.
There's a lot of different directions that you can go to, and so now can we do some further magic to figure out what's the right direction to go to in a way. And to find this a bit more informative. But just what it exactly means is, right, our loss function is a very bumpy one, right, with lots of minima, effectively. That corresponds to going different ways to the constraint surface. bunch of them are bad minima that I really don't really want to fall into. Then there's, of course, the minima with the smallest correction one, which might not be the one I'm actually looking for. There might be the secret ground truth golden minima that I would really like to have, right? This is the magic one that if I find this, I'm getting a faculty position. All right. And of course, if I have L1, but if I have an L1 loss, right? If I have ground truth claim, of course, this one would be easy and I would have no issues. And so how do I get there? And I'm changing slightly the problem. I'm going from a correction to a super resolution problem just because it was easier. Again, I'm a tiny postdoc with no engineering team, so I choose that problem. Because I'm doing an AM. Just why this also is an interesting problem is AMR. So when we need refinement, we can just add new grids, no problem, wherever we need them. And this is done with typically a normal polynomial interpolation. And so if I can do better than this is a very nice way for me to easily test things without ripping my code apart. Just saying, this is a very cool simulation. One of our codes, we did a higher dimensional general relativity, and there you can have black hole tori. They're highly unstable, but this is just a visualization that we have lots of refinement of our adaptive measures, and that's also our additional relevant noise source. They fall apart, and then because they have like a George Laflamme like fluid-like instability, and they just collapse into a spherical normal 5-dimensional black hole. And so now this is cool because now I can effectively, for these ones, it's really easy to have a ground truth without, for me, becoming OpenAI. So I can effectively compare how with L1 loss and with having a high resolution labels, what would be the ideal case. And one really cool thing is like, this is my learning curve here. This is my loss. These are the number of back propagation steps. I want to ask you which one is my new fancy loss, or which one is the ground truth loss using the L1? Anyone wants to go a guess? All right. Really surprisingly, like the physics loss is super, it converges super fast at least in the number of steps, spoiler. And L1 actually takes really long time to converge. And this is just my hypothesis is that just because we have this really highly informative loss, right? That there's so much information about the physics that we implement in the loss that the gradients are also highly informative. So actually we converge super fast. That instantly goes away if you plot the actual wall time, just because my loss is super expensive to evaluate. But at least I'm equally fast as having a high resolution loss. So this at least not too bad news. Now, what I'm finding here, and this is the L1 effectively. And here, this is a bit more technical, so bear with me maybe. Again, right, the orange one, just a reminder, is mine, and the yellow one is L1. And meaning, and if you go towards 0, you have the baseline and you have the ground truth, right? If you go towards 0, you go closer to the ground truth effectively. And if you have the baseline, if you go closer to the baseline, right, you can see our loss goes close to the baseline. And that is because we wanted to have a small perturbation away from our constraint surface, right? And so we get something which is very close to our constraint surface. However, the ground truth is a different minima. So this just confirms the issue that smallest correction is not the best correction. So how can we solve this? Like, how can we get there? So if I just randomly initialize, I'm just going to fall into the smallest minima. However, say I'm finding a smart initialization, which is somewhat close to the ground truth, I might fall into the ground truth. So smart initialization is the game. So I did that. I first ran with L1, found one network with the ground truth, and then applied it to a different simulation with a different mass for larger black holes using my loss. And so this effectively, this is the baseline again and the ground truth. And if everything goes well, the line goes down towards the ground truth using my loss. And unsurprisingly, it does. So effectively, by smartly initializing, I can force using my loss into the right solution. And however, if I'm too far away, this goes all away. If the mass difference is too big. But what does this exactly mean? So what does exactly mean? So if I have one simulation that just warms, if I use some supervised data, I can warm up my network and then just run a bunch of smaller simulations that effectively help it that are somewhat close by, right? And then maybe far away, but I can use a little bit of labeled data with a bunch of unlabeled data to get something which is closer to the ground truth effectively. So I can do the whole ChatGPT thing where I can use massive amounts of unlabeled data to get something much better. I need a bit of labeled data, but that's good enough. So cool, yeah. And so this was, first of all, this was the first ever application of deep learning to numerical relativity. So we showed there's a potential way of at least massively reducing the use of labeled data, which is, I think, the biggest hurdle to really implement this in a feasible way. And I mean, again, what I feel was really a big important to me, that this is something that now can be implemented with current state-of-the-art codes. So this is it's actually being useful. But yeah, all right. Are we doing time-wise?
Good.
Perfect. Yeah.
So thank you for this talk, and let's open it up to questions.
So okay, you showed that depending on, at the end here, you showed that depending on the mass you're testing on versus the mass that you used as your label, you could either get better or worse performance than just doing the sort of fully unsupervised thing, right? So is there a way of being confident that you can do better on average using some?
Yeah, no, I haven't done that yet. That's the next paper. This was only a small scale experiment, at least confirmed that the idea is not completely crazy. And yes, at the end, what I won't have to do is I have to fully deploy this on a large scale, which then requires now a bit of engineering effort for me to really do this. Yeah, that's the next step, next paper.
So let me ask you a question. So you've applied this to numerical relativity, but can this technique that you just showed us maybe apply to just general PDEs?
Yeah, I guess, I mean, as long as you, I guess, I mean, this is effectively a form of self-supervised learning. And if you have, I mean, I'm just effectively trying to find some self-supervised learning. I was trying some other way to get good features that I can use for the right downstream task. But roughly in that state, yeah. Imagine whenever you have constraints of anything that maybe we could use as a constraint, probably this might be usable. It works especially well just because these constraints are so strong, right? Like they're very annoying. If you do normal numerical simulations, they were I mean, just to get these simulations stable and keeping in constraint surface, this was already like many years and a major breakthrough to just get our normal simulations there. So the constraints are very strong, and maybe it works here especially well to maybe somewhere else like fluid dynamics or wherever. But yeah.
Any more questions? If not, let's thank Thomas one more time. Now it's time for the coffee hour.
We managed to talk about the multimodal stuff time-wise. I think okay. Balance it out.
No,
Nice talk. I hadn't heard anything about outside of your work.
Yeah.
Cheers.
Yeah, but I mean, like,
and.
Oh, wait, there's two.
well, maybe not.
Yeah.
Professor, well, of course.
I was thinking,